Hello, this is FRJH Racing, and I'm here to talk about some Robocraft physics, scaling, how we perceive the game, and actually how this influences how the game plays and how we feel and what it is like to play this game with its current scaling. And what I'm talking about that is there's a question posed today on the forums that was something that was actually asked way back, but I haven't seen in over quite a couple years, and the question is, how big is one cube? What is the scale of one of these blocks, one unit? And I'm going to conduct an experiment that I ran when I first approached this problem a couple years ago, and so I'm going to walk you guys through the process, and we'll answer the question together, and then after that's all done, we'll talk about how this changes the way that our perception of the game and how the game feels versus how the numbers look and all these other things, and how it actually influences balance and physics. So let's get right into it. First I gotta go to test mode, of course. So the test is set up like this. First, you get a robot that has a known length, and conveniently I made it the length that fits within one of these major units, I guess you could say, starting from this line and ending that line. So if you pull back a little bit, you'll see that it fits pretty much right in that cube. And there are 12 cubes in this line. So then if we also count how many of these major units there are, there's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 major units. So using this information, we can now put the whole experiment together. So if there are, here, I'm going to bring up this table that I made. So you have 12 blocks per unit, and we're traveling 8 units. So then the total blocks are going to equal the multiplication of that and this one. So that's 96 blocks. So then what we can also do is use our speedometer and find our top speed. So the top speed of this bot is about 200 and let's just call it 200 miles per hour. It's jumping around everywhere. So this is 200, and then miles per hour to meters per second. Let's just do 1 so I can actually use that math. So equals times 0.447, I believe. Alright, so now with this information, I can then time myself crossing from the beginning of the 8 major units to the end of the major units. So then what will that will give me the time times this times speed. Velocity times time gives you distance traveled. So when I put that in, I'm going to take a stopwatch and do a couple trials. So what I'll inevitably have is a distance, and then I'll also have how many blocks are in that distance, and therefore I'll know how many, how long one of those cubes are. So let's get going on this. Let's get this thing to top speed, and I'll try my very best to have an accurate time for the start and stop, because this is going to be pretty fast. This actually, to put in perspective, when I first conducted this this experiment in 2016, actually 2015, the top speed of this same bot was 96 miles per hour. So I would say we've come a long way, haven't we? So let's get started. I'm gonna start the clock right when I hit that first part of the test stage, and then stop it right after that. So let's go. Start, stop. 1.11 seconds. And so the distance I traveled in meters is equal to 1 times 199, and if there's 96 cubes in 99 meters, because it's meters per second I did it based on, then you can get to see where I'm going with this, but this equals this divided by this, and therefore you have it's going to be 1 meter cubed, 1 meter per side. So I can run this a couple more times, but really this is exactly what I got last time, and you can test this a couple other ways. And so what does this actually mean? So if you think about it, 1 meter for us Americans, I guess you can say, is so very close to 1 yard or 3 feet. And if you put that into perspective, 3 feet is, almost waist level, a little bit shorter than that. And in most cases, actually, I think 39 inches is your standard height for a countertop, if memory serves correctly. So if you can use those, relative measurements, 39 inches. Okay, I'm sorry. I remember the conversion to meters. So keep that in mind. I'm going to bring up this this Scion FRS I made, and it has a length from right here to about the bumper, from the end to end, of 25 cubes. I already counted it, so I didn't want to waste your guys' time. So that's, if we go back to this little calculator I got going on, we have 25 cubes, which equals equals 25 meters, or what's the meters to feet? 3.2 equals that. That's 3.2. And that's 80 feet long. However, that's of my car, of my depiction of the car, right? However, if we actually look at a real Scion FRS, it's 166.7 inches. And if 166.7, and there's 12 feet, 12 inches in a foot, let's divide this by 12, and we get 13.89 feet. So a real car is this big, and mine is 80 feet long. So if we look at just the pure scale, the scale, representation of what's going on here, we can divide that by this, and our scale is like a 1:6 ratio. So let's kind of extend on that further. What does this mean? So if I go into testing mode, perceiving this bot as like a real car. So using that information, if I know how fast I can go, which is, my top speed is 320 miles per hour. That's what it's topping out at, it seems. Which, I mean, that's a big number. 300 and it's more like 310, right? But that's 310 miles per hour. I mean, what car can you think doing that? Well, not many. And actually, the feeling of that, I would not say that felt like 300 miles per hour at all. I play a lot of racing games, and I can say that my perception of speed is much more accurate when I play a game compared to you know, some people that don't really play those kind of games. So when I play a game that has like a movement or something going on in relative scale, I have a very good perception of that. And I have, and actually a lot of us have caught it, that, you know, this whole feeling of speed, it feels really slow. And why is that? Because 320 miles per hour to us feels like 55 point, so like pretty much your everyday highway or overpass, or, you know, small highway in America. It's 55 mile per hour speed limit. So this bot is supposed to be like, you know, really fast, and this is, you know, fast for the game, but, you know, in actuality, I mean, I'm barely breaking 100. If I'm playing like a racing game, this is like, you know, child's play. But also, the thing is, my acceleration to my top speed is insane. It's almost instantaneous. Actually, I don't even think the speedometer can keep up with it. I don't remember that being a laggy thing. Actually, that's very new. But if you measure the acceleration, I can't do it anymore because of this whole laggy speedometer thing. I don't know why they did that, but the acceleration from 0 to the top speed, I can actually pretty much feel that. And I have my clock here, right? Let me reset it. So I'm gonna hit the gas right when I hit the start and go. Done. That's top speed. That was 1.53 seconds. So a unit of acceleration is a change in velocity over time. So that's why you'll see like meters per second squared. It's not squared time. It just means you have changed this many meters per second in this many seconds. So what I'm going to do is I'm going to break that down to miles per hour per second. So I changed from 0 to 320, 1.53 seconds. That's actually one second, and is this in decimals? Yes, it's 1.53. So let's divide that out. Gotta be careful with that. And my acceleration was 209 miles per hour per second. So then if I also convert the miles per hour, again, the meters per second, I can do with my unit conversion here, I have miles per hour per second, so I just have to convert the top of that equation. So then I'm going to divide this conversion right here, you know, because 1 mile per hour equals 0.447 meters per second. So if we do that, that's 93 meters per second squared. Alright, what the heck does that mean? Well, if we know that 1 Earth G, I know the game does not use Earth's gravity coefficient, but if we have 1 Earth G, that's 9.81 meters per second. That means this robot is pulling how many G's? It is pulling 9.5 G's, which is insane. That's the problem in this game, is that there's instant acceleration. Things are really, really big, and because of that, our perception is that things are really slow. But in actuality, they are slow to us. but they are going fast in the game, and they're represented as so. So the whole relative scaling of things, you know, kind of starts to blow up when you let's start looking at mass. So let's look at the mass of my bot. I don't know what it is right now. So my bot weighs 10,000 kilograms. Alright, so let's see, we got 10,000 kilograms. About, I'm not going to be all accurate with this. And one Scion FRS, in actuality, weight is that much in pounds. Pounds to kilogram. What was that? 2815. So this is a 1200, 1276 kilogram car in real life. So this is supposed to be, let's say steel, or let's do plastic. So 970 kilograms per meter. So if this was just a solid cube of plastic that was a meter cube, one of these weighs like not even, it's like 90, it's like a hundredth of it. So when it comes down to it, the game has very light parts, but also extremely, did I get the units right? Yeah, kilograms. Extremely huge. I mean, again, this car, if we, were to count this up, is 1, 2, 3, 4, 5, 6, 7, 8, 9 meters high. And if you divide that about one story, like a level in a building, is about 3 meters. So this car is 3 stories tall. This is like a really big house, like a huge house, like a mansion, or like any building that has 3 stories that you've ever been in. So and this wheel right here is being 1, 2, 3, 4, 5 cubes high. It's about like a room and a half. It fills your room. Just look up at your ceiling and think, oh, there's a wheel right there that fills up the entire thing. So if you think about all this together, the game has things that are too big and things that are way too light. But why is this? Why is this a part of the game? Surely there's a reason for it. And from an engineering point of view, and in the physics engine, this is actually perfect conditions for camera controls and comm assisted parts. For example, it reduces this phenomenon called overshoot. So if I had a system that, let's say that was my target and I was over here and I weighed so much and it had like a motor that spun me around, but its target was to stop me here, overshoot would be something like this, where I start going towards it and then I overshoot and I go back, and that happens. So a really bad overshoot is something that would look like this, and it would kind of converge to the point that the target is. However, when something is very light and also very big or has a huge displacement to go over, I'm not going to go into the math, and I already kind of did on the forums, but a lot of people don't care. It determines what's called your damping ratio, and basically all you need to know is if that is 1 or higher, it is over damped. And what that means is that same overshoot thing I was talking about, that motor, if I started an over damped system, would actually never reach the full speed of the motor's capability, and it also would just slowly approach the target. And then an underdamped system would have a little bit of overshoot, but it wouldn't cycle. It typically will not. Something that's critically damped won't like do more than a couple cycles of overshoot, and then something that is underdamped will have the cycling like I was talking about. So essentially, with it being very low mass, very large scale, we have a overdamped system. So this camera controls is one of these kind of actively targeting systems. It's a dynamic system that uses inputs to target something in a physical environment, the physics engine of this game. So let's just build a simple camera controlled bot. I haven't actually done this ever. I hate them. So, but it's so easy that it's gonna work on the first try, guaranteed. I don't even have to look at another one. I know this is gonna work. For a number of reasons, because I know how this. You know, I'm the one that brought you roll rockets. I think I would know how to make one of these stupid things fly. And if I don't, I'm gonna look like an idiot. But I think I will have no problem making this thing work. And then I'm also going to have the camera tilt on. So hopefully I have enough vertical thrust. Probably the one thing I did not get right. Oh no, this is good. This is just as easy as I thought. First try. Alright. So back to the whole overshoot problem. So I'm going to turn this bot to the right really fast, and if you notice, watch it overshoot. See that real quick? See that that little wiggle it did? But then it stabilizes almost perfectly. The amount of cycles it did before it was perfectly in line was, you know, less than one, I would say, or almost two. You can see, like, on a really good turn, it probably fires twice to compensate for that. And that damping ratio is close to 1. Critically damped means it will usually settle into its target after one overshoot and then not a second cycle. Something that's underdamped, again, is something that will continue the cycle until it reaches its target. And something that's underdamped would have been something that's slowly, like if I were to do that, it would like slowly move to its target. So in doing so, they've basically made this game very responsive, and it allows these kind of things to work, but you don't have to worry much about anything else. So all in all, that's why I also think that, you know, we might need to scale down the game a bit. In doing so, we're going to dampen this effect, no pun intended, but you wouldn't be able to make as responsive bots, you know, as this. And that whole mass density thing will also catch up with you, but also things will feel faster. The acceleration of something won't be like, you know, 10 Gs or whatever. You won't have to instantaneously accelerate to your top speed. And then a 300 miles per hour will feel, you know, instead of like 55 miles per hour, feel like actually 100 or more. So in just doing that, I think we can achieve more by rescaling the game. To reinforce my point a little bit further, this little bot right here would be about the length of the car I kept referencing, this guy on the Scion FRS. This car right here would be represented by this little bot, 4 cubes. That's it. And so if we zoom in a little bit and we try to, you know, drive this around, hopefully it behaves. Of course not, you know. And you know, it actually feels like you're driving somewhat like 200 miles per hour, because that's the actual speed of this bot. You know, it's a perceptual thing. However, it's also not as steady. It's not as stable. It feels like you're actually, like, you know, fighting against physics in this. But it's so small. I mean, this thing's only like 4 cubes that, you know, that's nothing. Also, mind you, that bot that I said was 10,000 kilograms was the size of like a 3-story building. To put that in perspective, one of my senior design projects was active suspension on a mining truck. I got to actually sit up inside of a mining truck, and we got to do donuts inside of the bottom of a abandoned quarry. And that thing was practically 3-story. It was like doing donuts in a building. It was the weirdest thing ever. And I think this particular truck actually topped out at about 50 miles per hour. So being in this massive building-sized thing and going 40 miles, an actual 40 miles per hour, felt like just outrageously slow. It was kind of, it was strange. You didn't know your size. And that's why, if, you know, full-size bots, you know, I'm talking about this right here. This is the size of about the mining truck that I got the ride in. Actually, let's see if I can bring up the truck I got to do this this thing on. So be there. There you go. So I got the ride in the top of that, and as you can see, that tire is what would you say, like 12 feet tall, 13 feet tall. And you know, you're sitting up there three stories in the air, basically. So you gotta walk up these steps. You know, it's like 1 story, and that's like 2, and then, yeah, I guess 3 would be up here. But you know, this thing's a monster. You take that going 50 miles per hour, and you felt like you're going very slow, to be honest. It didn't feel like going 55 miles per hour in a car. And then going 300 miles per hour, just like this whole relative scale thing, is just outrageous. But that's also to make up for the fact that, you know, going back to my, you know, thing here, you know, it felt like you're actually going 55 miles per hour when the game was telling you 320. What I also wanted to get at is that truck weighed 320 tons nominal when it was empty, and it had like a payload capacity of about 500 to 600 tons. So that's a lot of weight. That's you know, 600 tons to kg. It's 60,000 kilograms. Or actually, no, I'm sorry, 600,000 kilograms. And this one right here, I tried to make this point earlier, but I didn't, you know, have the example. 10,000 kilograms. This is 60 times, you know, actually a division of 60, like 1 to 60 ratio in weight, but it's the same relative size. So you have that as well, and you know, we'll look at the little car. Remember, the car was, you know, 1,200 kilograms, and this is 870. It didn't scale up, of course, quite as much. You know, in regards to the car, because this is more densely packed. This is just pure cubes, so of course it more dense. But at the end of the day, you have this whole scaling and density problem. Also, guns. I don't know if you remember back in the tier days, but this thing felt freaking giant. When you had a T10 round, it felt this big. Like, there was something with the camera back then, and just like the understanding of what was like a big gun, that, you know, this is what was big. However, if we look at bots now with let's see if I have anything with rails. Probably don't. I have like pretty much everything that's Royal Rocket, so, or a plane. Like that, this is like a standard size. You know, to us, this is normal. If you look at all my other bots, they all like take up the same amount of space. You know, if you look at all these, and if you go back, you know, these things are all the size of a freaking mining truck. They're humongous. So I hope that's kind of like giving you a better example of what's going on here, and yeah.